Hey everyone, this is the video for the part one of your milestone study packet. Make sure you're doing some practice with the USA test prep as well, and then also with this. Let's go through this, and then try it on your own, probably without looking at your notes. But let's see what you can do. Okay, so number one, a regular pentagon is centered about the origin, has a vertex at 0, 4. So center of the origin, vertex 0, 4. What transformation maps it onto itself? So basically, you've got a pentagon at the origin. It's got this vertex at 0, 4. What's going to put it back onto itself? Well, look at your choices. Reflection across line M. If you did it across line M, it would make this weird, thing like this, and that's not going to work, so not that one. Reflection across the x-axis, if you did that, this point would get reflected down here, and then you'd have some kind of thing like this, so that wouldn't work. A rotation of 100 degrees or 144. So basically what you can do is look at your angle of rotation right here. The way you get that is just taking 360, dividing it by the number of sides. There are 5 sides, so here. And if you did that, you'd get 72 degrees. So that means every 72 degrees, this top point would go to this point here. Well, I guess it's the same clockwise, so it would go this way. Now, it doesn't give you the option of 72, but it gives you the option of 144. If you multiply this times 2, that would be 144. So it would go once here, then once here again, and it would rotate back onto itself. So the answer here is D. So this is kind of an important thing to remember. What's the angle of rotation? Just 360 divided by the number of sides. Angle of rotation. 2. A parallelogram has vertices at blah, blah, blah. Which transformation maps a parallelogram onto itself? So, I can already kind of see a reflection across this line won't work because it would map this point up here. You'd basically get something like, let's see, this, right? If you reflected it that way. Same thing, if you did it the other way across this line, you'd have that point there. Okay, so what's going on here is you're going to have some sort of rotation. So reflection across x equals 2, well, that would put that point right there. So it can't be that. Reflection across y equals 2, again, that would put that point up here. It wouldn't be mapped onto itself. A rotation of 180 degrees about the point. So basically, this point would come down to here. But make sure you know that it's from that center right there, and that does work. The answer is C. D wouldn't work because if I did it from here, from 0, 0, 180, that would make this look like, kind of like this right here. It would put it down here in this quadrant like that. So to make it map back onto itself, basically spin it about its origin 180 degrees. Oops, sorry. Okay. Moving on. Which sequence of transformations maps ABC to RST? All right, so you do have to read a good bit, and you have to be pretty particular. One thing that will help you is if you understand what your lines are. So x equals only goes through x values. So what I mean by that is x equals -1. So you would go to -1 on the x-axis and think that is not going to go through the y-axis because it is an x equal line. That is x equals -1. Okay? And then y equals only goes through y value lines. So when it says reflect across, okay, imagine you kind of just reflected across here. It'd be 2 points away. 1, 2, 1, 2. That's point B. And point A would be over here. There's a reflection across, and then you've just got to look. Sorry for my drawing here. It's kind of hard to write on this tablet. And then look, translate 1 unit down. Okay, so if I went 1 unit down, that point would go right there. I need to map this whole thing onto RST. So it's actually going to be 5 units down because I would go from here to down here. I would go 1, 2, 3, 4, 5. It's got to be this. The other ones, translate 6 units to the right. It would never change the side that way. So I'd go over 6, and then 90 degrees would turn it like this. That would be C. Same thing with D. It would go over to the 6 and then do something like this. So, you know, you got to have a little bit of a imagination here. One thing you may want to do is kind of map that out on your scratch paper and then, trace them and see what it looks like moving them around. Okay. Figure A prime, I'll just call it ABCDF prime, is a dilation of ABCDF. So it went from the big one to the small one, went like this. Okay. Oh, sorry. All right, so it's going from big to small. The dilation, and it did it by a scale factor of a half. The dilation is centered at -4, -1. So from right here. What statement is true? All right, so one thing that can help out with this is thinking, why don't I just give, like, you could give lengths to your sides. So, AB over AB prime. So AB is this whole side. If it were 2, this would be 1. There's AB prime. If you look at BC prime to BC, you would have the shorter side, say that was also 1, and then call this one 2. You know, give your bigger figure the bigger numbers. That one can't be possible because, you would have gone 2 over 1 equals 1 over 2. That's not true, okay? These right here don't match up. The one that does, though, is B. AB over AB prime. What we just said, if let's say AB was 2 and AB prime was 1, because you halved it, say BC was also 2 and BC prime became 1, then that works. You went from bigger to smaller. All the other ones either go from big to small, and then like BC to DF, like this is this one side, it's bigger side to a smaller side. This is just one side to a completely different side. It can't be that. And it's the same thing here. Like, why would DF prime have anything to do with BC if this over here, AB is clearly saying bigger side to smaller side? So, just be aware of your ratios. Okay. Which transformation results in a figure that is similar to the original figure but has a greater area? Similar to the original figure but has a greater area. Okay, so you're dilating. Well, all of these, since they're dilations, are going to be like the original figure, but this one's going to be smaller, so it's going to have a smaller area. Same thing here. This one would be the same because you didn't dilate it. If you multiplied everything by 1, it wouldn't get any bigger. This would be twice as big, so a bigger area. Okay, that would be half as size, a quarter of the size, so the answer is D. In 3, in the coordinate plane, the segment PQ is the result of dilation of segment XY by a scale factor of half. Which point is the center of dilation? Okay, it's kind of, we've touched on this just barely, but basically you just go, like, say your point Q and T here, those are the ones that match up, and you just draw a line through them, and what ends up happening, it will give you that scale factor, like, or where the center of dilation is. So the center of dilation here is 0, or -4 is 0. And that's pretty much it. Because 0, -4 would be like down here. And like there's no relationship between those 2 points and these 2 points. Same thing with here. If you drew that line there, they would match up at -4, 0. So that's how you find your center of dilation. You basically just take 2 points, draw a line through it, and see where it matches up. Number 1, in the triangle shown, ABC is dilated by a factor of 2/3 to form XYZ. Given that A, start labeling now, is 50, B is 100, what is Z? Okay, if they are dilated, they're still similar, which means they have the same angles. So that's 50, this has to be 50, 100, this would have to be 100, and just double check. A goes with X, B goes with Y. That's 150, this has to be 30, so this has to be 30. So C. In the triangle shown, GH is parallel to DF. What's the length of GE? Oh, ratios. Just think. So, like, you have 6 to 4, and you want the length of GE, so you want this length here. So I did 6 to 4, so I need to do something to 3. And then you can cross multiply, you get 18. So again, I go from denominator to numerator. 4 to x, 4x divided by 4. X is going to be, 4 goes into 18 4 times, which is 16 with 5 left over, so 4.5. It'd be 2 left over, 2.0, so B. So just set up your ratios. Like, if you know you want GE, figure out that's what you want, call it X, and just say, all right, well, X over 3 should be the same as 6 over 4. Or you could have even said 3 to 4 will be the same as X to 6. And when I say X2, that means set it up as a fraction there. Use this triangle to answer the question. The triangle is not drawn here. I think it looks something like this. It's like this is parallel to that. This is a proof of the statement: if a line is parallel to one side of a triangle and intersects the other two sides at distinct points, then it separates these sides into segments of proportional lengths. Yeah, so basically you have this triangle that looks something like this. It's got two parallel sides, and we want to know which step justifies step 2. Let's see. Hang on one second, let me make sure my triangle's drawn right. Okay, so if you look at this triangle, this is the picture you should see, should draw. Draw one big triangle, IGK, and then draw a line through it called HJ. Should be a point here. And then you have these two triangles, IGK and IHJ. And basically it's asking what is going on here. So if you need to take a second, draw that triangle and pause and take a look. So what is happening here, though, is very simple. If you look, triangle HGK, right? Or angle HGK, H to G to K, this angle, remember your vertex is in the middle, is congruent to IHJ, right there, saying those are congruent. Then IKJ, IKG, right here, is congruent to IJH, this one. So all it's asking is, what justifies that? These two angles are just corresponding angles. So this is corresponding angles are congruent. And that's it for that. Sorry if your picture's missing, but that's all it is. It's pretty simple. Because remember, you can just slide that up there, and they're the same. That's called corresponding. So let's keep it going. All right. Parallelogram FGHJ was translated 3 units down to form parallelogram FGHJ prime. Parallel FGHJ prime was then rotated 90 degrees counterclockwise. Point G to obtain parallelogram FGHJ double prime. So it went through 2 translations. That's what the double prime means. Which statement is true? Let's see. It's a little fuzzy. I don't know why. Which statement is true about parallelogram FGHJ and parallelogram FGHJ prime? Let's see. The figures are similar and congruent. That would be the answer immediately because there was no dilation. So these were all rigid motions. Okay. And basically what's going on here is, since they're going to have, the same angles, and they're going to have the same side lengths because there was no dilation, they didn't get bigger or smaller, then they're going to be both similar and congruent. Okay, so I do make mistakes. Check this. This is true, what I said about rigid motions. And they are the same shape, and they are congruent, but the way we're going to keep these definitions very specific is these are congruent, and because of that, it covers the fact that they have the same angles, so we're going to say they're not similar, and just be specific and say that they are congruent only. So I apologize about that if I confused you. So basically, when you say you're congruent, it means all sides and angles are the same length. If you said you're similar, then that means your angles are the same, but you're not the same size. So you can't be similar and congruent. But if you're congruent, that means you have all the same angles, but you're not going to be similar. Or it kind of includes itself. So you can just be specific and say congruent. 2. Consider the triangles shown, which can be used to prove the triangles are congruent. I see here, angle, angle, side, angle, angle, side. So, angle, angle, side. What additional information is sufficient to prove that DEF is congruent to JIH? So, DE, all right, is congruent to JI, so that's what I'm looking at here. Angle D is congruent to angle J. So we got side, angle. If we had another side, that'd be great. So let's see what options they give us. ED congruent to IH. So if we did that, ED congruent to IH, that's not going to help us much because that would give us angle side, kind of. That doesn't work. DH congruent to JF, so DH congruent to JF. This actually works. If we said that this was congruent to this, then since HF is in both of the triangles, we already know that that's congruent to itself. And if I knew that, like, for instance, say this is 3. Okay. So HF is in this whole line here. And if I knew that DH was like 5 and this was 5, then I know DF would be 8 and HJ would also be 8. So they'd be the same. So you'd have side, angle, side, side, angle, side. You'd have 2 triangles that look like this. Side, angle, side, and then side, angle, side again. Sorry for my awesome drawings, but that's how it would be. So you would need that one right there. The other one's HG and GI. HG, like that and that doesn't even do anything. So HF and JF, HF and JF, that just proves that's that. That doesn't relate this piece. So basically make sure DF and this JF are the same. All right. In this diagram, CD is the perpendicular bisector of AB. The two-column proof shows that AC is congruent to BC. Which of the following justifies step 6? So CD is perpendicular bisector of AB. Perpendicular bisector. The two-column proof shows that AC is congruent to BC. So it proves this. Okay. What would justify step 6? Well, let's go through our proof and see what they tell us. All right, perpendicular bisector. AD congruent to BD. Got it. CD congruent to CD. That's reflexive property. And then that's right angles. All right angles are congruent. And then this is simple. This is side, angle, side. Side, angle, side. Those triangles are congruent by side, angle, side. And a reminder that if you're trying to prove pieces of the triangle congruent, you use that CPCTC. So, see. I'm going to start this for part 1. And begin uploading part 2 shortly after this. So.